Hello again, folks. Today we're going to be covering this in tandem, section 1.3 and section 6.3. These are both problem-solving strategies. I'm sorry. Today, if you look at the calendar, just to get in the habit of it, today is officially Thursday the 28th, and we are right on schedule as we should be. Okay. The packet that I have for you today, it's vast. There's quite a lot of pages. I'm going to show you the PowerPoint presentation I had made that is comprised of most of this. It's a little bit, it's like maybe 25 slides or something like that. So I try to chop it down, and what you'll see available to print, you could print out the PowerPoint if you'd like. It says PDFs. But what is the most important is in the packet that I have here physically. All right. I would encourage you, at least if you're looking for strategies, all right, to print this page first and foremost, and then this blank sheet, all right, immediately after it. Basically, I want to compile some English phrases that suggest that you will have to add, subtract, multiply, or divide. We'll start here. Here's some basic formulas. We're going to go through this, trying to utilize these, and I'm going to discuss proportions. That is basically what comes from section 6.3. Percent equations are just practical also. This is a little unnecessary at this point, all right? It's kind of overkill, that is to say, all right? But I want to explain this thing that I drew into a box here, because I think it will help you if you have any sort of conversion between units. All right. Here is a photocopy from, I think it was the back of a notebook I had at one point. These are all conversion factors, all right? They're written sort of horizontally rather than the traditional sort of fraction-esque style of writing them. But if you need to convert from one unit to another, right, this is where you might get that information most immediately. Expeditiously. All right. It's a diagram about ratios. Okay. And then there's the actual word problems. This is a slimmed down version of the PowerPoint. I didn't include all of the word problems in my PowerPoint, just the ones that I thought were the most important. All right. All right. So it's about half as many pages, I believe. All right. It's killing my printer, my home printer, because I gotta go buy ink myself. Let me get some water. And then let me fire up the projector here. I'll probably have to move it. Aim, Francis, there you go. Adjust the lens here. Hopefully this will be visible. It's about almost 10 in the morning. Not quite, 9:45. Unfortunately, it's a bit sunny in this side of the house. Let's see what I can do. That's too much. Bear with me. My extension cord is making this cumbersome. Alright, that is not quite within the frame here. That's better. And I wish I could make it a bit brighter, but unfortunately that seems to be the maximum. And my glasses, here we go. All right. This is for 113, of course, and as I want to re-emphasize the point, if you need anything to print, it isn't available right now because I have to update it this afternoon, but you would go to most likely Chapter 1 materials, and in the list here, right, of available PDFs, you'll see the packet that I have for you today. Right. Right. I'm going to go to my desktop because I have it already pulled out. Right. And let me go back to the top here, and I'll go through this. Okay. I stole this from Google Maps. This is the campus and aerial view. I thought it was pretty. Come on. I'm trying to adjust my blinds here. It's not really cooperating. Anyhow, word problems, alright? To ask people, what is your least favorite thing to do in math? Most often they would say, well, one of two things. Usually fractions is one thing, and then word problems is the other. These are, for the sake of this material, 1.3 and 6.3, my own personal strategy. Whenever I have to solve a problem, this is what I do. And I would encourage you, whether you take another math class or you take maybe a science course or a business course, maybe try some of these strategies. All right. First and foremost, right, I do the easy thing, right? The numbers are usually the most obvious thing because they're written as an Arabic numeral. So if you have to contrive either an expression or an equation from scratch, you're most likely going to incorporate the numbers that are in the paragraph or what have you, right? So zero in on those, circle them. They don't have to be red per se, but just draw your own focus to them because you're going to need to include them, all right? Then there are the actual operations, that is the adding, the subtracting, the multiplying, or the dividing. That is a little bit more nebulous because nobody ever seems to tell you, all right, well, this is what this means or this is what that means. That is why I want to, once I get through this, I want to try to compile basically a list for you, right? It won't be bulletproof, it's not going to be perfect 100% of the time, but at least it's a place to start, right? Then this is some other good advice. Try to, especially if you're talking about something that's a sort of a practical geometric question, right? When you're talking about areas or perimeters, draw a simple picture to summarize the information if they don't actually give you the picture. Most often in a geometry question of an area or perimeter, they would draw a simple rectangle or triangle or what have you, right? But if they're just merely describing it verbally, then do yourself the favor and try to draw it, all right? Same thing with points of location. If they're talking about point A, point B, point C, even if you have to modify it, don't feel bad if you didn't get it correct the first time you read it, all right? Try to draw a simple picture to summarize, right? Then there's this piece of advice, all right? I think most of us are probably intimidated and we feel that, oh, I can't just rephrase something, but do beware. If you've taken the SATs or any other standardized test in your life, you probably have seen those questions that are kind of gotcha, like they purposely try to deceive you, which I think is a bad way to teach people personally, but anyhow, they will give you irrelevant information. So bear that in mind. If the information is not really relevant, it's just there to deceive you somehow, then don't feel bad about rephrasing. Take a little artistic license, if you will, right? This is the most practical thing. If you have to write an equation from scratch, all right, look for the word is, because then you'll see in a moment, everything before the word is 1/2 of the equation. Anything that follows the word is the other half of the equation. So you're already ahead of the game, just zero in on that, it's pretty easy to spot, right? All right. Then there are these two last things. You could either borrow a formula, which is a famous practical equation, like the area formula for a rectangle, right? Or you could attempt to write one yourself, which, depending upon the unique problem, may lead you in one direction versus another. I'm going to try to sort of give you some examples of where to use what. Okay? That again is the information on this piece of paper. Alright, now let's do the kind of the interesting thing here. And I hope it's visible. If I have to, I will move this a little bit closer or a little bit further away. I can't tell which is really better. You know what? Ironically, to move it back is to make it a little bit bigger. I guess that makes sense. All right. Hopefully I didn't mess up the perspective too much. We had such gray days outside for the past week, and now unfortunately it is a bit too bright for my own good. Anyhow, we'll carry on here. Let's start with the more obvious phrases, right? Things that are very intuitive to you, right? Or anyone, right? You will recognize that we want you to add, subtract, multiply, or divide because they'll use the English equivalent of the symbol involved. So, for example, when we say plus, you might just see verbally or grammatically written the word plus, and then you pretty much know, all right, yeah, I have to add two things, all right? What would be the opposite of plus naturally? Minus. And then in the case of multiplication, I would say the phrase that is in English that usually is pretty intuitive insofar as a symbol is concerned is times, right? Which unfortunately gets you a little in trouble sometimes. For division, there is no word in English that seems to just simply say, that does without using the word divide. There's no equivalent, so I'm just going to leave that blank. All right. The next one, or the next row here, is in a slightly more subtle way, implying that you are going to add by using the name of the answer, if you will. All right. If somebody is talking about a sum, that implies that two things or more things are being added, and I am very purposely putting these things in a parentheses, right? When you get a sum, encapsulate them like that, group them, right? These are things that are grouped. Right? What is the similar phrase for subtraction? A difference. When you see that in context, know that you should subtract, and it involves at least two things, Okay. Sticking with this sort of system here, the name of the answer for a multiplication problem is a product. I'm putting these in parentheses again just to emphasize the point. You ought to group them. They don't really tell you that explicitly, so make that assumption. Sums should be grouped, all right? And I'm just putting the word sum here, and then I put these two question marks and a plus in between them to indicate that there's two things being combined. All right. The name of the answer of a division problem is a quotient. So if you see that in context, you know that you have to divide. There's a dud of a marker. All right. As we go down the list here, what you'll start to notice is that it gets less and less explicit and more vague. So don't be deterred. I'll go with this one. You might see the phrase increased by. That means to add, all right? And the opposite of increasing is, of course, decreased by. Decreased. These other two are a little bit more stupid. They're more plainly saying what their name is. Multiplied by and divided by. get out of the way of the camera now. Then I like these two especially. The next one's more vague. More than. And the subtraction less than. Beware. These two are counterintuitive. I'm going to put that up here. Counterintuitive. Because there's this word than tucked into it. Yes, it involves adding. Less, yes, it involves subtraction. However, very often you'll see it the way it's written in English. English gets you in trouble a lot when you're teaching math, believe me. You might, if you saw something like 4 more than 2, it's comparing these two things. There's a comparison going on here because of this phrase more than, alright? And you might intuitively go, oh, alright, that means 4 plus 2. And only because it happens to be addition, there's a commutative property of addition, you could get away with that. However, if you had 4 less than 2, less than, you cannot get away with writing this, right? 4 less than 2 should have the 4 behind the 2. It should be 2 minus 4 because it's less than this thing that it's being compared to here. Alright? And you might go, oh, that's trivial, why would you care? Because this will give you the answer -2 as opposed to +2, and they're not the same thing. They represent two different locations, alright? So just keep that in mind, alright? When you have more than or less than, they actually you should put the thing that is in the front of the sentence behind the thing it's being compared to. Okay. In the case of addition, you could get away with it only because there happens to be the math legalese known as the commutative property. There is no commutative property of subtraction, which means the order in which you write things definitely matters, and you have to put the 4 after the 2, even though it's up in the front. Okay? Then there's these two phrases. Of. If you see just the word of, it usually means multiply. When we get into percent equations, you'll see where that's practical. If, on the other hand, you see out of usually means dividing. All right? Like 3 out of 4 is implying a fraction 3 over 4. Or you might say 3 divided by 4, which means you get 0.75. Like 3/4 is 75 cents. All right. Let's see. When you hear about taxes, this is a little bit more up for debatable, but when you hear about taxes, it's an added cost to something. So I'm going to put it under here, under the heading of addition. Let's see. Interest. And let's see. Markup. And credit. And potentially commission would be another thing. You know what, let me exclude that. It's really not relevant in this case. But a markup is an added cost tacked on to something that's being sold by a store. And credit is what you get, say if you have a positive balance in your bank account. You know, if you have direct deposit, you get a credit, essentially, rather than a debit. The situation where you might associate with subtraction is when you're talking about a discount, which is a sale on an item, right? or, like I mentioned, a debit. Okay. Then there are these phrases. There are English words that simultaneously imply a number and an operation at the same time, simultaneously. Twice is an example of that. Twice means times two. Uh-oh. My computer went to sleep, sorry. Twice, and then there is technically another one, thrice, which would be times three. Okay. And then also for division, there is separately and maybe shared equally. I hope that this is visible. If not, I will upload the a scan basically of a filled-in table. But I think you might wonder, why bother us with this then? The experience, the actual exercise of writing something will help you remember it. That's really my only motivation for making you do it. Okay, now when we get to this point, it is up for grabs whether it's adding or subtracting. In fact, it might involve both simultaneously. When you see the word total, a total could involve credits and debits, you know. When something is spent, you know, or when you're talking about cost. All right, so kind of put them under these two headings, all right. This could be adding or subtracting. There's kind of a similar situation over here, and I'll kneel for this just not to block the camera too much. All right. You'll hear of ratios and rates. Rates. Okay. These are basically glorified fractions, if you will. They have a top and a bottom and a line in between them. Right? The thing is, when are they division, when are they multiplication? Well, I would say they are more to be multiplied. When you're using them. When you use the fraction, right, they're often multiplied. By themselves, though, they represent division. Because it's a fraction, and a fraction is a teeny tiny little division problem, even if you don't bother to do it. Like the perfect example of that, as I mentioned, was 3/4, right? 3 out of 4, right, is 3/4, right? Now you could convert that to a decimal by dividing the top by the bottom, right? 4 would not fit into 3, but it would fit into 30 roughly 7 times, and that would be 28, and the difference would be 2, and 4 would go into 20 exactly 7 times. 3/4 is literally 75 cents, right? This terminates. Right. Sometimes you bother to do the division and sometimes you don't. Right. Anyhow, by themselves, a ratio or a rate represents division. If you employ them somehow, it's often multiplied times something else. As I mentioned before, look for the word is means equals. It's not an operation, it's just a mathematical symbol. All right. Anyhow, I like to do this with people because it gives them a little bit more security. They go, okay, like I have some frame of reference and I have some resource to use when I'm trying to translate something that is verbal into something that is purely symbolic, purely mathematic. let me erase this. Insofar as formulas are concerned, these are some formulas that would be good to know, just as a citizen. And I'll try to give you an example of as many as I can. All right. There are many formulas for perimeter. This may be a little bit hard to see. So if you did print it, this is the third page here. I'm referring to this. All right. A perimeter, of course, there are formal incarnations of a perimeter. It depends on the shape. If you're talking about the perimeter of something like a rectangle, it's usually abbreviated P for perimeter, and then 2L plus 2W. But as long as you grasp the concept of a perimeter, that is the distance around something, you really don't need to have any specific perimeter formula memorized. You just have to convince yourself, well, it means A to all sides. All right. Area of a rectangle, on the other hand, is more specific, and you kind of have to use this. It might be abbreviated A is equal to L times W. All right. But this will work for both rectangles and technically squares as well. Then there's the Pythagorean theorem, right? The Pythagorean theorem is specifically for right triangles. Right triangles only, right? The sides are the things that are around the corner here. They're usually called legs. And sometimes they're abbreviated A and B, right? The dimension that is non-negotiable, though, is the hypotenuse, right? Which, again, because it's a little bit too sunny right now. The hypotenuse of a right triangle is the dimension that is immediately across from the box in the corner, okay? You could call this side B, you could call that side A, or switch one or the other, but that is non-negotiable. The dimension, whatever number it is always across from the corner. All right. Anyhow, as you can see, it's a dimension squared plus a second dimension squared is equal to the hypotenuse squared. That's not going to come up immediately, but it is practical information. These two are similar. These are examples of rates, or they involve a rate. Right? Speed is a rate, and miles per gallon is a rate. It compares one unit to a different physical unit. Right? You can calculate distance if you know speed and you know time, or you could algebraically rearrange these. Similarly, you can convert miles per gallon into a certain distance. As long as you know 2 out of 3 parts, you could figure out the third by rearranging. This is something that I just sort of threw together myself, and it might seem a little silly, right, the thing that I'm outlining here, but I think it is actually very practical, right, especially if you're feeling around in the dark. The total amount of something, if you are given that information, if they say the word, the total is blah, 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 5 feet, and then you know some chunk of the total, the known. If you subtract the known from the total, then you could figure out an unknown, right? It isn't too complicated, really. It just involves subtraction. But if you see that, and you don't really need to do anything too complicated, you know, consider using this, all right? As long as you know a total and some portion of it, whatever known portion of it that is a little bit smaller, all right, you could figure out an unknown amount. To say, well, this is where I didn't include this in the smaller separate pieces of this packet, and it's part of my PowerPoint. Here, I'll just show you the slide here. These are some techniques for when you're trying to write an equation from scratch. Like we had just discussed some formulas. Now, what if you had to kind of contrive something yourself? All right, as I mentioned, look for the word is in the sentences, and paragraph. If you can zero in on that, right, it's very useful, right? There'll be a bunch of words before the word is, and there'll be a bunch of words and maybe just a number, an Arabic numeral after the word is. Anyhow, this would immediately translate into an equal sign, which is not an operation, it's just a mathematical symbol, but it will be helpful, right? You will then try to convert whatever verbiage that you see on the left into the first expression. And whatever words or numbers or symbols follow the word is, on the right side, there will be a second expression. What's the difference between an expression and an equation? Basically, an expression is the building block, right? It can just be a freestanding number. It could be a letter. It could be some combination of the two, all right? But, all right, the equation is the whole kit and caboodle, right? If you see that you have an equal sign, you have an equation, right? Equations are made of expressions. Right. Next thing is technique, all right? You can do multiplication of fractions, say for example, for lack of a better phrase, brute force, or you could do it with a little bit more finesse. Here's what I mean. If you had something like 1/2, that's what I have here, that's getting kind of blocked out by the sun, and you multiply by 2, you could just do the top thing times the top thing and you get 2, and the bottom thing times the bottom thing and get 6. And then as an afterthought, attempt to simplify. After. There's no sin in that, you know, as long as the person actually does it. And strategically, you would divide by each of these things the same thing, by the GCF, that is the greatest common factor, the thing that the 2 is made of and that the 6 is made of, that is the same. The biggest thing that is the same. It is in fact 2. So in this case, this would reduce to 1/3, 1/3. That's doing it a little bit, you know, like tried and true, but it's a little bit more brute force, it's a little less finesse. If you were to employ this with a little bit more finesse, you would go, well, I see some similarity here. All right, there is a 2 below the line here, and there is, let me see if I can do myself a little bit of a favor. There you go. And there's a 2 above the line here. All right, because these things are being multiplied, legally speaking, you can get away with simplifying these out, crossing them out essentially, right? It is really doing this process of dividing by the GCF here and here, but without really consciously thinking about it. And then you would just simply be left with the answer. You know, the leftover components are the thing on the top and the thing on the bottom. This is true for numbers, as you can see, but it is also true for words and for the abbreviations for words. So if you had the same feature above the line as you have below the line, you could get away with basically crossing them out. All right? Feet will be canceled by feet. It is essentially saying what is something divided by itself. Most of the time, the only exception is you're not allowed to divide by 0. Go to math hell if you do that, right? If you divide something by itself, it really is just what quantity? It's 1, which oftentimes math people are lazy and they don't even bother to write that, all right? Anyhow, efficient is a nicer way of saying lazy, all right? All right, now let's do some examples. I don't really want to give up on my projector yet because these are all typed, right? And I'd rather not have to write them. Let's see. Let us do a couple of examples now. I have to, I will reluctantly move my board. Maybe I should give up and do that. If I perhaps turn it around, would it be better? I don't want to waste too much time, but I could, in theory, switch this around so that I'm blocking. I have two windows. I have a window here and I have a window behind my camera. So I don't think it's going to matter which way I turn it. It's still going to be kind of bleached out. This thing, the Kodak, although it was only $60, is showing its cheapness now. What thing? All right. Where's my papers? All right. Let's take a look at this. You get your feet wet. We'll do this word problem together. This is an example of basically sort of zeroing in on the relevant information so that you could write an expression or an equation, right, and then solve it. Okay. I'm going to X out of here for a moment. And then just go to this sheet, which is a slimmed down version of the same thing. Not too far away. Alright. See if the old towel here will help out. Fine sunny day it is. Is that any better? Not that much, is it? I figured. Hold on. Alright. Hopefully you can see that. And if you don't, please print this, and it's the same thing that is projected here. I would love to have a blacked out room right now, but I unfortunately am living in a house and I don't have curtains like that. Okay. Taking my own advice now, alright, I'm going to circle the numbers, alright, whether they're spelled or if they are abbreviated with the Indo-Arabic numeral here. So if you see 5, alright, I always like to write the symbol immediately above the word. 5 less than, alright. Less than, I'm going to put a box around it just to distinguish it as an operation. This is subtraction, right? But it is, remember, counterintuitive, which means that I'm going to have to adjust it in a moment, right? And then there is the number 3. And then there's this, again, an operation that says times, which means multiplication. And then we get to this phrase, a number, right? If we're writing an equation, we're going to have to probably incorporate a variable, right? So I always do what is intuitive. If we're talking about a number, then just, start with the first initial, right? An abbreviation for a number is n, right? The word is the equal sign. All of this junk that was up to the word is 1/2 of the equation. So I may start out rather sloppy, as you can see here, but I'm going to slowly but surely whittle it down into something a little bit more elegant. Right? Let me finish the rest of it first. The same as is the same as is kind of unnecessary syllables. They just mean the same thing as saying equals. It's redundant is what I'm getting at. As the number n increased by, this is another operation, plus, and then 7 is spelled out, so that's 7. To write it a little bit nicer, a little bit neater, I'll put it over here now. All right. If I start with maybe putting the equals here first, all right? I'm going to clean up the mess of the left side and then clean up the mess of the right side. If the phrase less than is really counterintuitive, it means that even though this thing that is in the front here, 5, would instinctively be 5 in front minus 3, what you want to do is put the 5 after, all right, the 3x, all right? So for right now, I'm going to do this. I'm going to put minus 5 on the left side of equals. 3 times a number, more concisely written, would be to not even bother write the multiplication x, but sort of bunch them together. It is implied that these two things pressed together are being multiplied. So you would have 3n minus 5, all right? English gets you in trouble when you're doing math, all right? I can personally attest to that as a teacher of math, all right? Because it has these comparative, counterintuitive phrases in it, all right? But don't be fooled. When you see more, you see less than, just go, all right, whatever was in front, I have to put it behind the thing, you know, counterintuitively. The other side is pretty straightforward though. So you have the same as a number n increased by is plus, and then there's just the word 7 spelled out. So you would have this. Let me erase some of the gobbledygook here. Just not to be distracted. And now we can go through the process of solving it algebraically. Right, we've done the hard part. We have contrived an equation from scratch. All right. So let's see. If we just work with what we have now, I'm going to turn that off. Come on. I'll turn this like so. I'm going to rewrite this up here because I need the space. If you feel a little rusty in terms of solving something algebraically, all right, I'm going to go through this pretty easily. All right, and then what I think I'll probably do is tomorrow is Friday. I'm going to record just a review of solving algebraic equations and simplifying perhaps for my 090 section. All right, it doesn't have any extra homework. All right, but if you need a little refresher, I promise I'll do that. Anyhow, I'm going to try to give you the information right now. Anyhow, but perhaps I could be more thorough, right, at a later point. When you solve algebraically, the best advice I can give you is this. You want to get the letter alone on one side. A more concise way of saying all of that is this. Isolate the variable. Right. To isolate a variable is essentially to get a letter alone on one side. Now you can see that there is a letter n here and a letter n here. So it doesn't matter if you put the n's on the left or on the right. Right? My instinct is to put them on the left side. But to do that, it entails two things. You move stuff over the equal sign. To move anything over and equals, you do opposite operations. All right, so if it says add, you're going to subtract. This is usually why a kid, when they're first introduced to algebra, probably around maybe 6th grade. In my own experience, it was more like 7th or 8th grade. But anyhow, they usually go, but that means plus, that means add, right? Why do you want me to do negative subtraction? Because we're not playing the game of arithmetic anymore. Now we're playing the game of algebra, which is a balancing act. It's very elegant in its own way. Very zen, all right? Anyhow, if I want to move the n over to here, I'm going to perform opposite operations. It has a slightly less obvious operation. If there is no sign written attached to this, what would you assume it is? You should assume that it is a positive. If there's no number attached to the letter, what number should you assume is there? You should assume that it is a 1. This is a positive 3n, really, and this is a positive 1n. It might be superfluous, it may be unnecessary to write those things, but if you're going to try to move stuff, I'm going to purposely write them. Positive 1, and this is a 3 over here, positive 3. What is the opposite of adding 1 with a letter n attached to it? Subtracting 1. If I do it here, I'm obligated to do it to the opposite side for the sake of balancing. That is the whole crux of this. You do opposite operations, but you can't get away with it unless you do it to both sides. Right? That makes it legal, right? Step 1, do opposite operations. Step 2, do to both sides. That makes it balanced. Right? Now, what's going to happen here is that similar to when you cross out a 2 above a fraction line and a 2 below a fraction line, is that you are, without really deeply thinking about it, simplifying. You are, in that instance, you're dividing something by itself and the effect is 1. In this case, you may not know what n is yet, but by sheer logic alone, you legally could just cross this out now. Because even if it is mysterious, it's something minus itself. So anything minus itself is what? It's 0. Do you have to put a 0 here? You don't have to. It isn't wrong if you do that, but it would be unnecessary. And then you have this. You got this junk left over here, 7. And you have this 5 left over here. And now I'm going to straighten this out. What is, these are called like terms. And like terms can be added or subtracted. They have the same letter. And technically there would be another condition. They have to be the same degree, which is the exponent, but it's not really written, so you don't have to worry about it. What is essentially 3 minus 1? 2. So now what you are left with is this. This is becoming a dud. So I'm going to put that away. 3n minus 1n, these are like, you do the actual subtraction. 3 minus 1 is 2. Just has an n attached to it. And then you continue with this, right? Because the objective is to isolate the variable, that is to get the letter alone on one side. Well, we've gotten it down to just one n rather than having an n here and an n there. But what we need to do now is to move the 5. So we'll do that now. I need the space. All right. What is the opposite of subtracting 5? I like to draw these little tables in case you can't tell. What is the opposite of subtracting 5? Adding 5 is the legal way. Right? So if you add 5 here, then you would add 5 here. Something minus itself is more obvious in the case of just a regular number. Will cancel, and yes, you could put a 0 here if you like, but it is superfluous. You don't have to do that. Right? What you will have now is this is a leftover, 2n. And then you have these things to add together. What is 7 plus 5? 12. Right? we're slowly whittling this down from something ugly that was started out as being verbal, and we're going to whittle it down into just a letter equals a number, right? But in order to accomplish that, in order to accomplish isolating the variable, we're still going to do opposite operations. In this case, we have to move the 2 to get the n alone. So, if again it is understood that two things pressed together, a number and a letter, is that they are being multiplied, how would I justify moving 2 from here to here? You do the opposite of multiplication. Now, the traditional symbol for division is, granted, the colon with the line through it, but in the case of algebra, they have the tendency not to write that. They'll just simply use the fraction-esque style bar, all right, to say this means divided. So if there's a 2 here and I'm trying to cancel, 2 divided by 2, I would put here, and then do the same thing to the opposite side. This is the Zen balancing act that is the essence of algebraic process. All right, it's a beautiful thing. Anyhow, there's a cancellation effect. In the cancellation effect of subtraction or of opposite positive negative, you end up with a 0 in both of these cases. When there's a sort of cancellation effect for division, you don't get 0, thankfully, you get 1 instead, right? Do you have to write 1 in front of a letter? Not if you don't want to, not if it isn't really concise. All right, you can, and there's no sin if you do that, but it would be more plain to simply say n. And then you have the guts left over here. What is 12 divided by 2? 6. This is the number that we were looking for in the problem. Okay, the number is 6. Let me get some water. Before I proceed with the next question, I'm going to somewhat reluctantly spin my little circus around here, all right, and see if I can avoid the sun in the process, because it's kind of screwing things up here. All right, so this may end in failure, right? Forever preserved on a video, but who cares? All right. I'll put this in for a moment, and you spin around, baby. That sounds dreadful. Somebody messing with you. There you go. You can see the lovely decorum of my apartment here. I got a staircase, isn't that great? And some paintings. Those are photographs of my family, actually. I wish they were paintings. Alright. And this is, I better not do that. I'll put this here for a moment. This sucks. Okay. Alright. That's my uncle's armoire from ages ago. Alright. That's not too horrifying. Now, if I do that, perhaps I can get this to be a little more conducive to learning. All right. Let's see if I can get that. And the other issue I have is that I'm competing with my sister. You probably hear some talking in the background. That is her doing her job. This is Corona life now, right? Alright, let's see, as long as I want it to be out of the frame here. Alright. maybe if I take my book out here, that's a wee bit better. Animal Farm. There's I'll link her up here. George Orwell wrote Animal Farm and also wrote 1984, which is a book about having people spy on you in your house, right? So that's apropos. And here's my brick. All right. I used to hold stuff. Slowly losing my mind, folks. Bear with me. All right, that looks basically okay. Amplify and rotate slightly. You could skip past this part if you'd like. I would never blame you if you did. All right. Chair. I don't even know what you call this piece of furniture, but I have it, and it's very useful. All right. Sort of an end table. All right. Rock and roll here. Back to reality. Now, let's see how this fares with the projector. Space. The final frontier. Is that aimed appropriately? It's still kind of sucky. Well, I hope that is better. It might be slightly. I will try to maybe enlarge that. To be out of the frame, yeah. Either. Alright. Continuing on, let's talk about this one. This is an example of where you might take a little artistic license and not be afraid to do that. Not to really digress, but let me just say this. As a person who has read, at this point in my life, many books on the same subject matter, namely math, they're not all created equal. There are some that are real stinkers, all right? And it's like, why had somebody wrote this? I'm like, how did you get away with publishing this piece of crap? Anyhow, not everyone is eloquent, all right? But they do have the authority, to write a book. So take that with a grain of salt, all right? That's the correct phrase. Just beware, is what I mean. Not every textbook is a good book, all right? I don't dislike ours. I think it's fine, right? But some sentences have too much information in them. So even though you're a student and you may be like, inclined to just be, polite, which is nice of you, right? Take a little artistic license if it is necessary, as long as it is correct. Rephrase it so that it gets to the point, and then translate into an equation or what you need, right? Here's an example of too much information, right? The 5-speed Jeep Cherokee gets 23 miles per gallon, right, on the highway. How many gallons of gas would be needed for there should be a name here, first of all, 667-mile drive from El Paso to Dallas, Texas, right? The numbers involved here are definitely important, right? Except one of them. The thing that is a description of its transmission, right? A 5-speed Jeep Cherokee really isn't relevant, right? So don't feel bad about, and if you bought the book especially, crossing out irrelevant information like that, okay? And go away, I don't need this. Now what you might do instead is just say a car gets 23 miles per gallon, right? There's no description of it anywhere else about what type of driving it is, you know, city driving or highway driving, right? I would assume that from El Paso to Dallas, Texas, you're not driving on back roads, you know, you're on a highway. So you don't really need to worry about the highway either, all right? If a car gets 23 miles per gallon, a car, vehicle, whatever have you, all right, then how many gallons would be needed to travel 667 miles? That is really all that is needed in order to solve this problem, right? Again, you can't be, you don't want to be like a bull in a china shop and just, you know, just ramrod through something, you know, roughshod. But you can't, how shall I phrase? The flip side of that, there's a phrase that's escaping me. One has to be balanced, all right? Essentially is what I'm getting at, all right? You can't be, you know, just, you know, blindly rushing into something, but you can't be intimidated either. You know, there's a balance there, right? An equilibrium. Anyhow, this is all that you need. You're going to use 667 and 23 miles per gallon. You might take advantage of some other tidbits of information here. You see the word per, all right? And I really should have added that on my sheet. Per is suggesting that this is a rate, right? MPG is how you might see it on a sign, right? Advertised for the car's you know, gas consumption. Just like MPH, miles per hour, might be on a street sign, right? But it really, in math world, would look like this. Per is this line, right? Over 1 gallon, right? When you see two different units, you have a rate officially, right? They measure different things. One is a distance and the other is a volume. Right? Anyhow, of the formulas that I had suggested earlier, this is one that might be useful to you, right? There are problems where you may have to rearrange the 2 out of 3 parts here to solve for something other than distance, but this is already pretty much good to go, right? We're going to borrow this essentially. So let me get rid of that for a moment and write the formula rather than contriving one. Distance is equal to MPG, miles per gallon, times a number of gallons. It's really just two things multiplied together. If you were in a science class, they would probably be a little bit more anal retentive about the units and such. So I will be, just to show you, right? First of all, we want to know how many gallons. So we're going to pull some algebra here. We're going to move this stuff around, right? If I want to solve for gallons, I got to get the phrase gallons alone on one side. So I'm going to do the opposite of multiplying MPG, which is to divide by MPG. This will cancel here, even though it's not a number. All right, and then if I've done it here, I'm obligated to do it here, and vice versa. Right? That means that a rearranged incarnation of this would be that gallons is equal to a distance over an MPG rating. The distance involved is 667 miles, so that's above the line, right? The MPG rating is 23, So that would be below the line like so. I'm going to erase this now. And then write it a little bit more cleanly. Right? Gallons is equal to 667 miles, this is with the unit now, over 23 miles per gallon. It would, if you spelled it out entirely like that, look like so. A fraction underneath a fraction, if you will. Don't be scared, all right? If you want to translate into, rather than having it stacked and using this line to imply division, use the column with the line symbol. What that would be is like this: 667 miles divided by, that's this line here, 23 miles per 1 gallon. All right, and now you have something that is a little bit more conforming to the style of a fraction problem, a division of fractions problem. Just to remind you, when you divide a fraction, there's a procedure involved, which is essentially keep, change, flip, right? That means that you keep the first thing exactly as you see it. You change the operation somewhat ironically to multiplication, and then you multiply by the reciprocal, which is this fraction flipped. That essentially means now, I'm only erasing this because I need the space, that you have this. This will transform into 667 miles. I'm going to put a 1 under it to make it look like a fraction. It's not hurting it. Changed to multiplication and then compensated for by using the reciprocal, this flipped upside down. 1 gallon over 23 miles. All right. I'm using the abbreviation for miles. All right. Insofar as the number is concerned, you could glean the number immediately upon inserting the 667 here and the 23 here. No sin in that. But if you're in a, let's say, a physics or a chemistry class, or maybe business or economics, you would, or maybe biology even, you would have to be a little bit more anal about how the units would actually cancel. That is really the only reason for this exercise. All right? Remember what I said before. If there's something similar above the line and below the line, you can cancel them. All right? That works for numbers, it works for words, it works for abbreviations for words. All right? Miles and miles canceled leaves you with the unit that you wanted. All right? This is another way of validating your suspicion about how it should be answered. All right? Anyhow, to get the number, it would be really 667 divided by 23, in which case you would get the outcome here, 29 gallons is the answer. Okay. Let's see. I'm going to turn my projector back on for a moment, and I'm going to show you something that is not included in this slimmed down packet of word problems, but I felt that I should just mention it right now. What time is that? Now we're in? Okay. I'm going back to the comprehensive thing here. All right, this may be a little hard to see. Let me erase the gobbledygook here. This is an example in which you might want to draw a picture to summarize information, and it doesn't have to be, you know, a masterpiece. It just has to convey the information. All right, so humor me. Mary travels from Columbus to Indianapolis and then on to Springfield. 3 places. All right. If the distance between Columbus and Indianapolis is 168 miles, I already circled it. All right. And the total distance, I put a box around that because it implies the operations. Mary drives 351 miles. What is the distance between the other segment, Indianapolis and Springfield? It is a little verbose, right? So what you do is you go, all right, I'm talking about 3 distinct locations, right? The total distance, if I were going to try to explain this to myself, right, between 3 points. The total distance, actually rolled away. Come on back, there you go. The total distance is from this point to the outer point here. And that is apparently 351 miles, right? If the starting point is Columbus, I'll just put a C here for Columbus. Right? And then she goes to Indianapolis, so I'll put an I as the middle point. And then on to Springfield, which is an S. Right? Between Columbus and Springfield is apparently 351. Right? The distance halfway, vaguely, is between Columbus and Indianapolis. That's this segment from here to here. That would be 168 miles, right? So as you can see from this very simple picture, this is only a chunk of the entire trip, right? It's a segment of the whole. This is another opportunity to use a basic formula that if you know the total, and it is explained to you, 351, it would be, if you subtract out the known portion, that is a segment, this will tell you the unknown segment. And it's 2 techniques at once, using a basic formula and drawing a picture to simplify. Picture is worth 1,000 words. It's not a very good picture, granted, but it does summarize what is written verbally here in English, and English is frequently confusing. So, anyhow, sorry for the superimposed lettering here, but I think you get the idea. All right, essentially, that's twice you did that now. All right, if the total is 351, I'm essentially going to subtract 351 by 168. Right. And in that event, the remaining amount should be the unknown segment from Indianapolis to Springfield. The answer to the question is 183 miles, it should be. Notice that they at no point explicitly stated, hey, subtract these 2 things. But you can infer that from the picture. And the basic concept of that, a whole minus a portion of the whole will be the other half of it. It's not really correct to say a half per se, but you get what I mean. The other smaller segment. Well, in this case, it's a larger segment. All right, moving on. Let me go back now to the packet that I have here. This question, right? There was a picture in my PowerPoint that is a farm barn, basically. So when I went to give you this slimmed down version of it, I left out the drawing because it consumes a lot of ink. Why is it doing that? That's weird. Okay. All right. Okay, a rancher must fence in a corral, right, as shown would have been a picture that looks like this. Somebody's property basically looks like that, and there's a farmhouse, barn next to it. Something like that. Okay, and there are in the drawing these dimensions that are written: 300 feet from here to here. Fence posts, if you will. 275, 200, 200, and then 475. Right. This is something that is going to take advantage of the concept of perimeter. Perimeter being the distance around something, and the usage of a rate. A rancher must fence in a corral, as shown, this terrible drawing here. Fencing is required across the barn no fencing is required across the barn entrance, so you don't have to worry about the complete enclosed circuit here. All right. If the fencing costs $4 per foot, this is a rate, right? Because the word per is in it. It's a glorified fraction, right? All right. You could then write this as $4 per 1 foot to use abbreviations. Right? What is the total cost of the fencing? Well, it's not explicitly stated once again, but what you could assume is that, well, if it's $4 per foot, I would need to know the total feet. And the total feet is just another way of saying this perimeter. So you can infer that, well, I need to add 475 to 300 to 275 to 200 to 200. I have to take these figures and add them all together, right, firstly. And if you do that, what do you get? You get 1450. 1450 feet is the total perimeter from here, well, from here to here to here to here to here to here, right? Just not across the barn because it's an entrance for the animals, presumably. Anyhow, if I were to clean this up a little bit, this would be, I'll put it up here, $4 per 1 foot times 1450 feet. And just to make it look like a fraction times a fraction, I'll put a 1 under it. This is another instance where the units would justifiably cancel because there's feet above the line here and feet below the line here. And then realistically, it's just 4 times 1450, 002, which is $5,800 is what it should be. Okay. Now, what I'm doing here is I'm using something called the conversion factor. And so what I'd like to do is show you another diagram here. Just pay attention to what is in this gray box here. If you have a problem that talks about 2 different units, and just bear in mind the units have to measure different physical quantities. They can't be just like, feet and inches, because they measure, those 2 things measure the same physical quantity. Just one is a larger increment than the other. What I'm saying is, when you're talking about completely different units, right? One above the line and one below the line, right? You have something called a conversion factor, right? the sheet that I included in the packet that has this information from the back of a notebook. That's a good one. Is for cooking, 2 pints equals 1 quart. These are not written in the style of a fraction, but more or less they're written in the style of an equation. But if you wanted to, you could translate any of these things into something that looks like a fraction. And once you do that, it becomes part of a handy sort of tool, an equation, for translating something from one unit into another unit. That is really the whole point. A conversion factor translates units. So as in the case of the last problem, I was talking about, this is the conversion factor without calling it that, $4 per 1 foot. You might want to say that dollars is the unit essentially. Right? It would be not really correct to say that, but it's behaving that way. All right, it's not measured. But the foot is definitely a unit. So if you wanted to figure out total cost, you put the dollar on top and the thing that you're going to cancel underneath, right? If we had, in this case, it was $14.50 for the total number of feet here, this cancels this, right? The units cancel justifiably and it leaves you with what you want. Then to get the number, it would be the thing on top times the thing on top, right? We're going to come back to this probably later in the semester, but it's starting to show itself earlier on, which is why I'm mentioning it. All right. Now, before we get into the next word problem, there is a discussion about proportions that I have to go through. And I think what I'll do is I'll turn off the projector at this point. Spin bulb. Let me pull the blinds in. Right. Now I have the opposite situation where it's too dark. How much more can I move this stuff around? Let me see what I can get away with before I start spinning anything. I think there's a few more word problems that I really would prefer to project. So I'm going to kind of stick with where I am. My body is blocking the light. All right. Anyhow, let's discuss this. This is from section 6.3. It is the portion of section 6.3 that is immediately important. All right. Proportions. And since we just had broached the subject of conversion factors, I'd like to sort of compare the two because they kind of look alike, even though they're not really the same thing. They both involve things that look like fractions, basically. What? Conversion factors, if you're going to subscribe a purpose to them, I alluded to this before. Their purpose is to convert. One unit into another. I'm squeezing it in here, I'm sorry. All right. And there's that model, right? The model is essentially, this is how it looks. It looks like a number times a fraction, meaning that there's an obvious top and an obvious bottom. The thing that I've sort of encapsulated in the parentheses here, that is the actual conversion factor, right? This is a generalization here. I'm being very non-specific, right? Just bear that in mind. There's a fraction, that's the conversion factor, whose job is to convert from one unit to another, times whatever some figure, some number with another unit attached to it. A proportion is essentially, if you're going to subscribe a purpose to it, to upgrade, for lack of a better phrase, or to downgrade dimensions. Think of a photograph as an example, such that there is no distortion. I don't know if you've ever played around with Microsoft Paint, right? But at least in the oldest versions of Microsoft Paint, it would allow you to draw something and then you could enlarge it by changing the horizontal and the vertical number of pixels. All right, anyhow, if you don't do it quite consistently, you could morph the picture, right? If you had a photograph of a person's face, all right, they come in standard sizes like a 5x7 or an 8x10, whatever have you. Those dimensions are, is it really quite bright? Decided just not to make your face look wider. When you purchase a larger size of your school portrait, you don't want it to have your face or your head stretched one way or another. Anyhow, proportions would help you determine, what the correct dimensions ought to be. Yeah, hello, here for my college exam today. Anyhow, how do they look? They basically involve a fraction, well, two fractions. They look like a fraction set equal to a second fraction. Right. So make that distinction. When you're dealing with conversion fractors, you're pretty much dealing with one fraction. When you're dealing with proportions, you're dealing with two fractions that are opposing one another. One is on one side of equals and one is on the opposite side of equals. All right. The model that you usually get in a textbook is something like this. You see A over B is equal to C over D. Never mind those letters, just realize that these are four voids that you would fill in with a number. A number here, some other number here, some other number here, some other number here. And always, if it's truly a proportion problem, an equals in between them. All right. Now, as far as procedures are concerned, I don't want to use green, that never works. You might involve, as you had seen before, the process of, shall we say, cross-simplifying. Which is to basically cancel units or some such thing, right? Diagonally like this, That is not quite the same thing, though, when you're talking about proportions. What you would do as the process of solving them is in this case, cross multiply. Cross simplifying, which goes on here, is really division without consciously really thinking about it. Cross multiplying is multiplying, right? Just diagonally as well. If you know that you're dealing with a proportions problem, just do this. Sort of encapsulate things diagonal, connect one thing on the bottom to one thing on the top. And the other way, right? You're going to multiply these two, and you're going to multiply these two. All right. Let's do an example. In a nutshell, like anything with algebra, and it's the beauty of algebra, if you have the majority of information, you can always figure out algebraically what the missing chunk is. Turn the projector back on here, and I'll show you this other relevant problem. Okay. I like this problem because it finally, even for my own sake, explained how is it that biologists can determine, how many animals of one species or another are wandering around in the wild without going up to each one. They're hard to find too, and counting each individual one. They don't do that. Right? What they use is a proportion, essentially. So, let me again take my own advice and sort of zero in on certain information as I read this. A biologist wants to estimate the number of moose that are in a wildlife preserve. She captures and sedates 250 of them and then tags them, all right, each of them. I believe it, and this sounds cruel to me. They put like something in their ear. All right. She captures and sedates 250, tags them, and then lets them go. All right, releases them back into the wilderness. After several months, the biologist recaptures 120 moose at random, and then notes that of those, 4 have tags. All right? Assuming that none of the moose have lost their tags, approximately how many moose are in the preserve total? This is an indirect way of counting how many moose are actually wandering out of the wild by using a proportion. So, I probably shouldn't turn off the projector, but let me start with this. We're going to use a proportion. Equation. Which means that we're going to have a glorified fraction set equal to a glorified fraction. And we have 3 things out of the 4 total that we need. Now I'll just put them over here. 250, 120, and 4 have to be somehow incorporated into this model here. Let me turn off the projector now, because it's kind of getting in the way. This is why having an actual classroom is always welcome. You have much more board space. When you're trying to set these up yourself, the best advice I can give you is be consistent. Right? There's probably more than one arrangement that would be fine, but you want to be consistent. Right? That is, once you've decided what goes above the line, make sure that you do that consistently across the board here. So if we're talking about, let's just say, total moose, or rather tagged moose, let's make that consistently the number that is sitting here and that's sitting here. Usually what happens is that the first fraction that you're filling in is the first sentence, and the second fraction is the second sentence, or at least something that follows it. So in this case we have take moose, and what I'll make is the bottom figure is total moose. Initially, the number of tagged moose was 250. The total number of moose is really what the question is, so I'm just going to put X here because it's unknown known and unknown. Okay, now again, take my own advice and be consistent. When I'm trying to decide where to position the 120 and the 4 over here in this second fraction, I'm going to be following this model here. The number that are tagged is 4 in that situation, out of a total that is 120. Right? I now have an algebraic equation known as a proportion equation. Right? One fraction or one ratio, whichever phrase you prefer, all right, sitting next to another by equals. Right? And the process, you could attempt to simplify this fraction first if you want to, or just go straight forward. For it. So the process is to cross multiply, which means that you're going to write 4 times x on one side of equals, and then 250 times 120 on the opposite side. You could just punch this into your calculator, but let me give you some advice as well. Especially if you're in a science class, you might spare yourself a little bit of trouble, especially when it comes to rounding and such, by superficially multiplying. That is, kind of park them next to each other with a dot in between. Don't do the actual number. Right? Leave it like that. You can totally get away with it. Right? It isn't wrong if you crunch the number down to whatever it is, but watch what's going to happen. If you go through the same process as before, which is to solve algebraically, you're going to isolate the variable via the process of opposite operations on both sides. So, if these two things just got multiplied and you want to justify getting this alone, what is the opposite of multiplying by 4? Dividing by 4 here, and then dividing by 4 the whole side here. This is strategically going to cancel or simplify it down to what? 1. You don't have to bother writing 1, you would just write x, which represents total moose in the preserve. And over here, you now, if you want to, can simplify. Or you could just punch these into your calculator and it should be fine. All right. A lot of times I do these things without a calculator because it's a good mental exercise, and I recognize certain relationships. There's a relationship between 4 and 12, right? So if I divide by 4 here to simplify and divide by 4 here to simplify, this ends up becoming 3, which is really 30, right? And then there's another mental math skill here. Non-zeros, 3 and 25. 3 times 25 is 75, right? How many zeros are involved in this? 2. 7,500. So indirectly, a biologist can predict that there are in fact 7,500 moose wandering around in the preserve without having to go up to each one and going, ooh, a moose, a moose, a moose. All right. All right. Now we're going to get into percents. So
they're called meese, by the way.
Meese, yeah. Many meese in the woods is many moose in moose. More here. Let me just point out something. There's a sheet I'll make available that includes this discussion on ratios. A ratio is
what we think of as a fraction is really the more general phrase would be ratio. All right, a fraction is a specific type of ratio, as are rates. All right, a ratio is any number sitting on top of any other number. All right. That situation with the units involved are rates. And then you can, if you want to, you can have a unit rate, or you can have something called a unit price if you're talking about money. How it looks grammatically is like so, right? There's usually the word to in between two things, or out of. Right? So if you see A to B, you could write it as the first thing stacked on the second thing. Out of is same situation. Right? I don't know why I chose the opposite colors here, because I'm kind of a dodo, but I should have been consistent. Anyhow, when it comes to a fraction, right, it's a little bit more stricter criteria, right? There are no decimals in the top figure, there are no decimals in the bottom figure. Overall, if you converted the fraction to a decimal, that may be what the combined result is. But individually, the parts, the numerator and the denominator is what we would usually say, they can't have those characteristics. No decimals in the top, no decimals in the bottom. Then we would call it a ratio instead of a fraction. Okay. Now let me review some things about percents. I was getting breathy. I need more water. There are, there's a subject known as percent equations in math. Right. And percent equations really come in three varieties. Right. There are what they refer to as the part equations, or sometimes they called it amount. And then there's the base equations. And then there are the actual percent equations. That is to say, you're looking for the part, you're looking for the base, or you're looking for the number that is the actual percent. In terms of the math involved, part equations are purely arithmetic. What you see is what you get, right? You're just gonna, if you have to multiply if it says multiply and nothing else. These two, when you're looking for them, are really algebraic. And of the two, this one has an added step. The percent equation itself, the literal percent equation, the one in which you're looking for that number, is two-step versus one-step. How can I tell that you're dealing with one or the other without it being explicitly stated to you? You will see some suspect phrases, right? If you see the phrase, is what, right? In this arrangement, you're probably looking for the part, which is a portion of the whole amount of something. If you see of what, then you're probably looking for the base, right? Which is basically the original or whole amount of something. If it says what percent, it's pretty obvious in that case that you're looking for the number that is the actual percentage. The kinds of things that would be a part equation would be a sales tax kind of calculation, or a discount. All right, or markup. All right, or a commission. Okay. These are actual dollar values. Right. Sales tax is a dollar value. A discount is a certain amount of dollar value, right? The kinds of equations or problems that you're looking for the base are things that there's this phrase, a principal. If you're looking for the principal in context, this is a fancy way of saying an original amount of money invested or borrowed. If you hear this phrase, percentage rating, or percent rate, right? These are the number that is the percentage. There might be an interest rate, right? Or a markup rate, or a commission rate, or a tax rate. Right. And in this instance, they're not a dollar value. Right? It's basically either a fraction or it's a decimal. Right, that you're looking for. Right, now let me give you an example of each one of these. If you're a little concerned about things like commission or markup, is you're not familiar, I think everybody knows sales tax and discounts because you go shopping at some point, right? A discount is when something is cheaper, and sales tax is when something is more expensive. Markup is an amount of money that a store, adds to an item. So, like for example, if you went to buy a calculator from Staples, it will be a different price than, say, if you bought the calculator at the school bookstore or some other resource. All right? Why the difference in prices if we're all talking about the same item? Because those stores all have a business model that has a different markup, meaning that they're going to try to maximize their profit by maybe making something more expensive than it has to be. Right? A commission is when you say, if you work for a car dealership or you're a real estate agent, to encourage the employee to supposedly work harder. They would say, well, if you sell a lot, then we'll give you a chunk of the sales, right? This is a portion, a reward, basically, all right, for selling a lot of something. Now let me give you some examples. I need to erase this from the space. And I'm going to do the same problem from 3 different perspectives, so you see the relationship. All right. If you see, I'll try to isolate myself a little bit here. You see something like this. 50% of 20 is what? It has this phrase, is what. It's probably a part. You're looking for a portion, some chunk of the whole, not the actual whole. This is great if you're trying to learn to translate. Because what you can do is you can directly translate pretty easily. Is what symbol equals, right? Of is what operation. Because it's just of, it's usually just times. That means that the junk that is sitting around it just gets dropped down next to those things. So if there's of 20, then you could say it's times 20. It says is what, you can just put a letter here temporarily if you like. 50%, you have two options. You could either translate it into a decimal, which is just 2 decimal places over to the left, always 2, or you can convert this to a fraction, right? 0.5 is really 1/2, right? That is something that's going to come back in a subsequent chapter, but you don't really have to worry about it too much. If you just want to get it done with your calculator, just make 50% 0.50. You know? Otherwise, you could say to yourself, well, it's really 50 over 100 because that's what percent literally means. Percent, the symbol with the line and 2 O's, is really the denominator of 100. Okay? This 50 over 100 would reduce to what? A half, right? This is essentially asking you, what is half of 20? The answer would be 10, right? That's why I say that this is pure arithmetic. It's just this thing times this thing. There's no trickery here. Half of 20 is 10. If you're looking for a different chunk, though, a different portion of this question, it will be phrased slightly differently. It would be something like 50% of what is 10. When you get a question like this, of what, all right, as opposed to is what, know that you're looking for the base, all right, which is, again, a fancy way of saying, well, maybe not so fancy, the original or whole amount of something. You can still translate it into the symbols that you need to. Right, and here's how I would do that. Is equals, 10 is sitting here now. Of what, you could put, you know, times a letter, choose a letter. Let's go with N again, maybe. And then do the same thing. You could either make this 50% 0.5, or you could make it a fraction. In this case, it would probably be easier on you to just make it 0.50. This is an example of where you would really need to employ algebra rather than just straightforward arithmetic, because the numbers are not on the same side. There's a variable here rather than on, by itself. So you would have to do opposite operations to solve this. What is the opposite of multiplying? Dividing by the number here, 0.5, and then whatever you've done to this side, you do to the opposite side. All right? Something divided by itself, even if it's ugly, cancels into 1, and then you're left with the thing you're looking for, n equals, and then you could punch this into your calculator, or you could straighten it out. This is asking you to divide 10 by a half, right? 10 divided by a half is really 10 times 2, which is really, you could probably tell without even doing the calculation, because I wasn't too creative here, it's 20, right? One more of these. What if you're looking for the actual percentage? It's pretty straightforward in that case. It would say, what percent of 20 is 10? I would still nonetheless translate what is verbal into what is mathematical. Is equals, of is times, 20 is in between, 10 is on the end. In this case, just because you're talking about a percent, you might just opt for a different variable. It doesn't have to be n anyway. So I'm going to call this P for percent. You have the same situation here. This is going to employ algebra rather than straightforward arithmetic, because the numbers are not on the same side of the equals. It's just not the way they work out. So you do opposite operations. How do you do that? Well, what's the opposite of multiplying by 20? Divide by 20 here, divide by 20 here. 20 divided by itself cancels, it's really 1. P is left over, that's what you're looking for. And then you have 10 over 20, which you could type this into your calculator, 10 divided by 20 if you like. Or you could pull tricks, cross out pairs of zeros, and you have the answer 1/2. But what is 1/2 in the style of a percentage? That's the only thing you have to worry about. You could reason to yourself, well, I know since Ziegler was kind of a dummy and just used the same thing over and over again, 50, 50, 50, that this is going to be 50, or do the work. All right, you can convert a fraction to a decimal first if you feel more comfortable, and then convert that to a percentage. That's usually the flow of logic. Sometimes you could skip over it and go to this directly, and sometimes not. So this is the process. You would divide 1.00 perhaps by the thing on the bottom, 2. How many 2's can you fit in 1? You can't, 0. How many 2's can you fit into 10? Exactly 5. And then it would cancel, and they would have a 0 here. All right. That is just a decimal though. We want a percent. So how do you convert a decimal to a percent? You divide by 100, all right? And the effect is that this, this decimal, multiplied by 100, which means that this decimal point will move this way. So you end up with P is equal to 50% formally in the style of a percentage. Okay. Converting from a decimal, from a percentage to a decimal is dividing by 100. That is why the effect of this decimal point moving here to the left is ending here on the left, because you're dividing by 100. If you multiply by 100, the effect is that the decimal point moves this way towards the right. Okay? Let me give you some formulas and then we'll do a couple of examples and then we're done. Okay? It would be appropriate at this point to mention some formulas that happen to incorporate a percent. So let me show you that. There's simple interest formula. Which looks like this. You know what, let me do one other thing too. As I mentioned, sales tax, which I'm just going to abbreviate as ST, is a type of part equation. So it's going to be a percentage times the price of something. An amount of money times a percentage, it would be in the style of a decimal most likely. Right. If you're talking about a discount, this again would be a percentage times the price of something. If you're talking about a commission, this would be a percentage times an amount sold. I'm putting the cross line here to indicate that this is an amount of money in each of these cases. And if you're talking about markup, it's the dollar value that is markup and not the actual rate of markup. Then it's a percentage times the cost of something. I don't know if it's really appropriate, but I'm using the word cost in place of the word price, because cost is in theory how much something was bought for by a store, right? Whereas the price is what the store is selling it for, Cost of the item times the percentage, that is the markup rate, will be how much the markup value, the actual dollar value would be. That is something that would be added to that, and then it would be a price, I believe. It would be appropriate to say there. All right. anyhow, these are all just multiplication problems. You're just calling these things a different thing. You know, it's just a percent times a dollar value, a percent times a dollar value, a percent times a dollar value, a percent times a dollar value. They're all part equations essentially. All right. Now, as far as simple interest is concerned, simple interest is an amount owed or earned, all right, on an original amount. And we're talking about money here. I should say, in addition to. Okay, and it's abbreviated as I for simple interest equals P times R times T. It's just three things multiplied together. Let's see. P is principal again, which is again the original amount of money. R is a rate, which is really a percentage. And T is time, but time has to be time in years. It's very strict that way. It has to be years. So if you get months or something like that, you have to convert it to a decimal of so many years or a fraction of so many years. This is a little bit hard to see, so let me rewrite it. Time in years. Okay. Then there is this other thing. Markers are dying. I just bought them. There's a percent. This is interest, incidentally. Simple interest, I. There's a percent of change, or in a science class they would call it percent of error. And it's equal to a difference between two values that is something minus something else divided by the original amount times 100. Multiplying by 100 makes this fraction ratio equal to a percentage. Just realize that you have to subtract two things first, then you divide by the original number, the original amount of something, and then you multiply by 100. Okay. Let me show you this question, number 7 here. Floyd takes out a loan for $3,500. He then pays simple interest at 6% for 4 years and 3 months. All right. How much interest does he pay? All right. Of these two, I would use obviously the simple interest formula because it's even named in the word problem. So let me erase a little bit. Erase a lot. And we'll fill this in. All right, maybe I'll turn the projector back on now. We're going to use this number and this number and these two. And the formula is I equals P times R times T. The original amount is $3,500. That is the principal. Let me give you one piece of advice. When you're talking about money that is borrowed or invested, it is most of the time a nice round number with zeros. And it would actually be to your advantage, believe it or not, to write these in the style of a fraction, and you'll see why in a moment. You just put a 1 under it. Right? The rate is 6%. 6% is really 0.06. But if you write it in the style of a fraction instead, it would be 6 over 100. Right? That's going to be to our advantage when we put that in the calculation here. 6 over 100. And then there's this, 4 years and 3 months. Remember, 3 months is a fraction of a year, right? So if you think about this as being 4 is the whole number, it's 3 out of how many months are there? 12 months, right? Now what you could do is reduce the fraction and then simplify it. I hope it's not getting blocked too much. 4 times 12 is 48, plus 3 is 51 over 12. So I'm going to use the improper fraction here, 51 over 12. Now the reason that I bothered to write these in the style of fractions is that I can simplify a lot diagonally. Right? Yeah, you could use a calculator, there's no sin in that, but you could also be strategic. Here's a perfect example of that. Nice round zeros here, and underneath it here, zeros, 2 here, 2 here, goes away, right? There's a relationship between this thing above the line and this thing below the line. They have a GCF of ideally 6 is the greatest common factor. Yes, they're both even, you could use 2, but 6 is better. 6 divided by itself is 1, 12 divided by 6 is 2. So on the bottom you have 1 times 2, technically. Right? And on the top you have 35 times 1 times 51. Right? 35 and 51 is kind of an ugly number, but it's a little bit easier to work with. Anyhow, you end up with 1785 divided by 2, and the result is this. The amount of interest only is $892.50, I believe, yes. Okay. This is employing a formula and taking advantage of cross simplification techniques. As long as we are multiplying, you can get away with doing things like that. All right. The last of these word problems that I thought would be worthwhile is this one. The sum of 3 consecutive integers is 87. Find the integers. There's very little information in here, but some of it is implied, in a subtle way, and you can figure it out. There's techniques for that. If we're talking about a sum, especially a sum of 3 things, that means that there are 3 things, mysterious as they may be, that have to be added first and foremost. All right, there isn't anything else to it. It isn't times anything else, but I would still nonetheless start with encapsulating these things like so. 3 consecutive integers. If something is consecutive, what does that mean exactly? Consecutive means one thing immediately is followed by the next thing. One thing immediately follows another. So there's not much, if they're consecutive integers, and we're not talking about evens or odds or anything like that, one is immediately after the other. To say that something is an integer is a way of implying that it's a whole number that may be positive or negative, right? What I would encourage you to do as a strategy is this. I'm going to pull up my PowerPoint presentation instead for a moment because I have it illustrated there. When you get a situation like this, you're going to try strategically to interpret everything into one letter, into one variable. So again, if it's talking about an integer, intuitively the letter you might choose is I. It doesn't have to be, but that would be, logical at least. All right. Anyhow, if you're talking about three distinct things, let's just say that the first one is the variable in question, is I. If they're consecutive, expressing the second one using the same letter would be to say that it is I plus 1. If you're talking about now a third consecutive integer, how far away is it from the original one? The third would be I plus 2. Right? There's another problem that I didn't include in the sheet, but I'll just scroll up for a minute to sort of glance at it. If you're talking about like odd or even things, an odd, you just choose one letter, and then when you're talking about the consecutive odd number or perhaps the consecutive even number, just add 2 to it because that's how far apart they are, right? Consistently into infinity. All right. Anyhow, we have the sum, and it is equal to 87. All right. So I have these three things that have to equal 87. I'm going to get rid of that and turn this off. All right. So, the first thing is the letter I. The second thing is I plus 1. The third thing is I plus 2. And they still nonetheless equal 87. Even if you don't start out this way, it's fine. I'm going to put these little things in their own little universe here, encapsulate them, just to make it obvious that this is the first thing, the second thing, the third thing. The reason that you have to interpret everything in terms of just one specific letter rather than two different letters, and it isn't wrong if you start that way, X and Y and Z or whatever, is that if you only have one equation, you can't solve for that if there's three different letters going on there. There's something called systems of equations, which in theory would require you to have two equations simultaneously, or three, or more. And then there's a whole class called linear algebra that's about that. Anyhow, if you have one equation, you need one letter, strictly one letter. Right? Now we're going to combine like terms again. Right? You can add or subtract like terms, as long as they're the same letter. And technically the same degree. That would be the exponents, but you don't have to worry about that. Right. How many i's are there? If I got rid of these parentheses now, and I just had a bunch of stuff being added, how many i's are there? There's three of them, right? So what's the abbreviation for that? 3i would be the most concise way of saying that. What also is left over here? There's this plus 1, and there's this plus 2, which coincidentally is the same digit, but it's plus 3. And lastly, there is this, equals 87. You now have an algebraic equation, which is maybe a little weird because it has the letter I as opposed to X or N or some other letter. But we can go through the algebraic process now. You know, clean this up just not to get distracted. If this is reduced to 3i, just so up here, just so I don't have to hunch. 87. Right? We're going to try to isolate I, which means get it alone on one side, via opposite operations. And we have to do this to both sides to make it legal. Both sides of what? Both sides of equals. I always like to draw little tables like this because to me it makes it a little bit cleaner, a little bit easier to work. I'm going to move the 3. All right? What is the opposite of adding 3? Minus 3. What's something minus itself? 0, which you don't have to bother writing, and in fact it would be more practical not to bother. All right. What's 87 minus 3? 84. What's left over? 3i. Still have to isolate this I. What is the opposite of multiplying by 3? Since they're pressed together, we assume that 3 is times I. Division of 3. And if you did it here, if you want to make it legal, you can get away with murder in math as long as you're consistent. If you did division of 3 here, you're obligated to do it there. Okay? These reduce to 1, which you don't have to bother writing, which means I is equal to the outcome of 84 divided by 3. 3 fits into 8 roughly twice, which is 6, and the difference is 2. 3 goes into 24 exactly 8 times, which means that the first consecutive integer is 28. But then the second is an additional 1, which is 29. And the third is an additional 2, which is 30. These are your 3 consecutive integers, which if you check them, 28 plus 29 plus 30 gives you 87. Okay. Now, the last thing, which I'm not sure why it got thrown in here, but it's kind of a brain teaser. It's not part of this packet, but I'm going to show it to you right now. It's called Magic Squares. I noticed in the MyLab homework that they had this little brain teaser in there, so it's worth mentioning. Essentially, if you can imagine a tic-tac-toe, it's not really that, but it kind of looks like a tic-tac-toe. That is completely encapsulated in a square, right? And there are, I'm not being too creative here, numbers written into it, like this. The condition, if it is not just a box with boxes in it, if it's truly a magic square, right, whether diagonal, in a row, or in a column, or diagonal.
Okay, give it a try. I'm glad it's working so far.
The sums are all the same. And the brain teaser, the mental exercise that is involved is that they'll give you some numbers and they'll say, here, arrange these uniquely into, you know, the squares so that across this way there's a certain number that is the same across this way and across this way. Here's an example. You can see this has little to do with the problem-solving techniques, but it is somehow included, so I'm going to mention it. You might be, as an example, told to using the numbers, digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. Construct a magic square. Remember, these are the conditions, that whether in a row or a column or diagonally, the sums all have to be the same. So, let me draw a box, and we'll try this. The procedure that seems to work is to go that's green, it's not going to show up. Put in numerical order. It already is in numerical order, right? To find the middle number. These are already in numerical order, right? But if they were jumbled, put them in numerical order, right? What is the exact middle here? 5, right? Put 5 in the center. Right. I'm going to start out with trying to basically arrange the other numbers in sequences of 3 with 5 in the center. That'll make it a little bit easier. Okay, now you know that you can only add things, because we'll talk about sums here. Try a mix of a small number plus 5 plus a large number, right, to find the sum. Right. If you went with the smallest thing and the largest thing, right, what is 1 plus 5 plus 9? I need the space. One plus 5 plus 9 is equal to 15. Let's try the next smallest thing. 2 plus 5 plus 8. Is it the same thing? We'll see. 2 plus 5 is 7, 7 plus 8 is indeed 15. Right. Let's try this one. 3 plus 5 plus 7 is 8 plus 7 is indeed 15 again. Good. And then 4 plus 5 plus 6. Right. 15 seems to be the sum that we're looking for. So, with 5 at the center, all right, let's use this one first. All right, we got 5 here. You could probably put 1 here and 9 here, but the book suggested putting 9 here, so I'm going to stick with that. 9 plus 5 plus 1 across this way is 15. Right. Now try this one. 2, 5, and 8. My instinct initially was to put the 2, the 5, and the 8 here. But what decides that ultimately is whether the things that immediately follow it will also work. In other words, that they will also add up to 15. And what would happen if you put 2, 5, and 8 here, yes, it would be 15 this way. But then that would force you to take these things and they wouldn't quite work. So the way that it ends up working is like this. Maybe put the 2 here, the 5 here, and the 8 here. Right? You want to have this kind of balance between small number, all right, something, and then a large number. Right? You don't want small and large, because they're not going to be the same. They're not going to make 15 basically. All right. So this took me a couple of tries myself. It's kind of a fun mental exercise. All right. Let's go here though. 2 plus 9 plus what would be 15? Let me just cross this so that I have accounted for that. That's 15. 2 plus 9 is 11. So in order for it to be 15, what would this number here have to be? 4, right? So a 4 would go here. How would I connect 4 and 5? What would have to go here now? Four plus 5 is again 9. 9 plus what would be 15? In this instance, you'd have to use 6, right? A small number, a large number, and the thing in the middle. Okay, and that's 15 this way. Now let's see. Did not use 7 at any point. Where would 7 fit? All right. I can't put 7 here because if it was 8 plus 7, it would already be 15, and then 4 would kind of screw it up. So if I put 7 here, this is fine. 2 plus 7 is 9, 9 plus 6 is 15. If I put 7 here simultaneously, 7 plus 5 is 12, then what would go here then? Um, 3 it would have to be, right? And since I haven't used 3, that makes sense. Right? That's 15. So everything is filled in. It seems to make sure all the numbers are used. 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all used. Let's see if all the slashes here are correct. That's 15. 15. I got to check this one. 4 and 3 is 7. 7 and 8 is 15 as well. Diagonally, 2 and 5, 8 is 15. 4, 5, and 6 is 15. It's good. All right. Again, there's a little bit of strategy that unfortunately you kind of bend the rules a little bit when you do a unique problem because it depends on what the numbers are. But in general, whatever the middle is here, right, try a small number and a large number in tandem, all right? Not two small things, you know, not two large things because they're not going to get up to the same consistent figure, whatever that consistent figure happens to be. Okay. Let's see, we're at 2.5 hours in. I think I'm going to stop. And I'll upload. Let's see. All right, that was section 1.3 and 6.3. All right. So ideally what you want to do for homework is do section 1.3 and 6.3. I believe that section 6.3 has a part 1 and also a part 2. I gotta look at that just to verify, but I believe that is the case. So it's technically 3 things that you have to do. Okay? Somebody asked me a natural question, is that, oh, well, what do these do? Are they immediately due? No, you have until, I believe, let me look at my calendar really quick to verify it. Up to the day of the first test. So you technically have until February 9th to do this. all assigned homework, my labs, will be due by the evening of February 9th. All right, you would see this in Canvas, it's already written there. Anyhow, you don't want it to get away from you though, so I'm like, don't wait please until February 8th to go, I'm gonna do 10 things. It's not gonna happen, all right? It's too much involved, right? Even to explain these two sections, look at me, it took me 2 hours, right? So try to pace yourself, all right? You have the weekend, all right? I'm gonna try to record a video, all right? It's explaining algebra just for the sake of clarity. But start your homework is what I'm getting at. You could turn it off and come back to it, right? It's not going to be a concrete grade until that day, you know? Okay? All right. Thank you for sticking with me. Be careful out there.